Hi guys, 8D, carrying on here in Unit 8, page, what is this, 141. So we're going to get into some new material, but I want to just, we want to run through this example here to show you something kind of a unique example of using the AC method for factoring. So we know when we use the AC method, we need an A, a B, and a C. So I'm looking here, I only have two terms. I've only got a binomial. All of the ones that we've done before now, we've had a trinomial to give us our A, our B, and our C. So there's really no problem here, but you're going to have to create the middle term. So this is x squared, and then how many x to the first powers do we have? None. 0 x to the first powers minus 9. So now we have our A is 1, our B is 0, and our C is negative 9. Our AC, our product, is negative 9. So we can have a pair of negative 1 and positive 9, positive 1, negative 9, or a negative 3 and a positive 3. I need to add to B, which is 0. So there's only one of these pairs that add to 0, and it's this guy right here. So when I go split my middle term, I'm going to write it x squared minus 3x plus 3x minus 9. That gives me my 0 term in the middle, but we've just rewritten it. So when I go to do the rest of the AC method, I'm going to factor out an x, and I get an x minus 3. I'm going to factor out a 3, and I get an x minus 3. Then I'm going to factor out the x minus 3, leaving me with an x plus 3. And this is my factored answer for x squared minus 9, where we started. So what you will begin to notice is that when you have the difference, meaning you've got to have subtraction, of two squares, two perfect squares, you can factor it really simply and quickly by just writing A plus B. So here I'm noticing that I've got an x squared. The square root of x squared is just x. The square root of 9 is 3. I can write x plus 3, x minus 3. And what happens is these middle terms, to get this 0, you can see this is a minus 3x, this guy right here, and this is a plus 3x. And when you add those together, they cancel each other out. So we'll work a few of these. I also want to talk to you about perfect squares. So if you'll just make a note here, these are integers that are squared, or variables that are squared. So in other words, 1 is a perfect square, 1 times 1. 4 is a perfect square, 2 times 2. 9, 16, 25, on and on and on. But also, x squared is a perfect square. That's x times x. X squared, y squared is a perfect square. That's x times y times x times y. X to the 4th is a perfect square because that's x squared squared. X to the 6th is x cubed squared. X to the 8th is x to the 4th squared, on and on. So we're going to do a lot of factoring with these perfect squares. So this is going to be a factoring pattern that you see quite a bit in algebra. So let's notice that this, of course, x squared is a square, a perfect square. And it is a difference. So I've got a subtraction sign, and 25 is a perfect square. So once I've decided that all three of these conditions are true, I have a difference, and I've got a perfect square here, and a perfect square here, I can just write down x plus 5, x minus 5. You take the square root of both of these. The square root of x squared is x. Square root of 25 is 5. This guy right here, x squared is a perfect square. I have a difference, and 81 is a perfect square, is the perfect square. 9 is the square root. So it's going to be x plus 9, x minus 9. So I think I'll stop this video at, what, 5 minutes or so in, and then I'll come back and we'll do some more examples that, that have a little bit more to them than these. Thanks for watching.